Okay, so this is the third of three little 20-minute, 30-minute lectures that I'm given for week 13. This is lecture 25, and what we're going over is quiz 2. And so far, what we've gone over is just some of the fundamentals of radiation transfer from chapter 1. Chapter 1 or chapter 2? I think it's chapter 2. Yeah, one's kind of just an overview. So we've gone over that. We've gone over the G's being radiation. There was no difference in the book between G and G naught, and then the Q's being the heat transfers. Went over kind of a prickly thing just now, the difference between K and R. Went over the fact that K is, in fact, intrinsic, R is extrinsic. Showed a little blue board example. If you've got blue board, they have the same K value because they're the same material, but if you make one thicker, it's going to have a bigger R value. And then finally, we solved problem, I guess that was problem 6 on quiz 2, and actually came up, calculated the thermal heat loss coefficient K for a given situation. Okay. EBAD was used a few times in the text, and I'm astonished that you actually got this thing right without any, because any little typo would kill this thing, but earth equipotential bonding and automatic disconnection of supply. Do you guys remember what that was from the book?
I believe I got that off Google.
Did you?
Got it out of the little book, I think.
Oh yeah, it was in the little book.
Yeah.
It was in the
I think the Piggott book.
Oh,
Yeah.
Piggott? Oh, yeah, that's right. All right, I'm like, I had to shift gears there for a second.
And I think
Yeah, that was a wind question.
I must have had a misspell or something in there.
Yeah, I'll go through and grade that, make sure everybody got credit for it if everybody's closed. Do you remember what that was, though?
No?
well, this ability to ground the whole system, right? Basically.
Yeah, it was something I was not that familiar with. I guess I'm still not. I mean, when we were over there taking down the wind turbine, and we noticed that it was grounded, and what's not clear to me is if it's grounded in order to protect it from a lightning strike, which is something you want. I mean, you don't want the lightning to come in and just fry your motor, or if it's in there in order to keep static electricity from building up in your motor. That could also be the point too. I apologize. I do not know the answer. It's just something that I looked into. Let's just look it up though really quick. I don't mind going to the Google and doing some
Well, I know on
interpretation.
housing electricity, it's you're grounding everything that could possibly shock somebody.
Mm-hmm. Yeah, I mean you want one big fat common ground for every
And it goes to
light
at least
switch,
2
metal.
8-foot grounding rods.
Mm-hmm. The automatic disconnection of supply. That's the part. I'm not sure if there's some kind of circuit in there that pops open. Let's see what these guys have to say. KHU. ADS, automatic disconnection of supply. I mean, it might be similar to a GFCI. I mean, a GFCI does open a circuit if what goes in does not come out.
Or it's more of an AFCI,
AFCI?
arc fault
Mm.
circuit interrupter.
Mm-mm.
GFCI is if,
Oh, I'm with you. Yep.
you know, like in a GFCI, it's detects a minute
Correct.
change in the current.
It's leaking into ground.
Right.
Yeah,
And then an arc fault is an actual, you know, short,
a bigger one.
Yeah, big.
Yep,
you know.
yeah, yeah.
So if there's a short, then that would, you know, kill somebody.
Mm-hmm. Okay, so if live wire touching a metal case, the earth will facilitate automatic disconnection of the main supply. So does that mean if you've got, let's just look at it here for a second. So here's Earth, and then let's just say you've got your turbine here, and this is, let's just say, metal tower, and you've got your turbine up here, generator, and so you start making high voltage. And I guess the point is, if this high voltage then arcs to that, which should have been touching the ground, it must be a system where you've got a here's your EBAD system, your EBAD circuit. It sounds to me like, is it take the electricity and put it somewhere? Is it just like pumping it somewhere else, or?
It sounds to me like it's just, you know, it's a safety. So if you've got voltage going into your metal
Yep.
housing or whatever, it's
Yep.
a safety mechanism so that if somebody touches it,
Mm-hmm.
they don't ground it. It's already grounded by a much better pathway for the electricity.
Yeah, is it that, or does it automatic
The fault.
disconnection? Yeah, it sounds like it opens something up somewhere.
So maybe, yeah, I don't know. That part's.
Earthing, connecting parts. So obviously, earthing is sticking everything to the ground, and then once one big thing is earthed, you can just bond other things to it. Let's see what else these guys have to say. Two main types of bonding: main equipotential bonding and supplemental bonding. Connect all the incoming services such as water. Okay, fine. So all of the stuff coming in is all the plumbing, electric is together. Then supplemental would be like the metal tower, the other electrical wires in your turbine. That's your supplemental.
So is the EBAD is just the talks about the whole, like, okay, you're grounding everything together to get everything together. It's just the whole practice of grounding.
Yeah, but I keep thinking that the automatic disconnect is I don't see it right here either. So when we nail it with this guy, sounds like the automatic disconnect part, though. The AD
Right.
is like a relay that opens somewhere.
Would that just be your main panel?
Breaker? Yeah,
That's
maybe.
really the only place you find disconnects.
Yeah,
And if you do have a short in the system, it's gonna
yeah.
short your breaker.
Well, I'm just going to get a little creative here and assume or guess that somehow this guy is connected to ground too, and that if it senses there's some local current, coming down here. So you've got, it's the current that kills you, right? Not the voltage. So the current's coming down here. If this current then finds its way up there through its ground, it would then, in my opinion, if I were running the show, I would take this guy, and once it's been detected, shut the turbine down. Because essentially your turbine is your main, like your turbine is your primary sensor. It'd be like, okay, shut the dang thing down, because it's just pumping juice into the ground through the tower. Someone else is going to come along, touch the thing, and if they're more conductive, then who knows how this is sneaking through. There's got to be some water or whatever. If you're more conductive, then the electricity is going to go with you. But if the EBAD does its thing, and it's connected up here, it's going to shut that down.
Well, if the electricity,
Mechanically shut it down.
yeah, if electricity gets to the ground, it's grounded. It's good to go.
Yeah.
So
It should be.
So it'd have to be attached to your EBAD
Yeah.
system
It'd
by
have to be like
wiring
in
or piping.
series
I-
before it hits the ground, right?
Well, I mean, I think the ground itself is conductive. I mean, we can go out and stick an ohm meter right in the ground, and we'll get some number. And well, it deserves some further research. But it looks like if for whatever reason this path, where your electricity would normally just be going, through your cable and out to your grid, through some insulation. If instead it went down through the tower, you'd want that disconnected. Anyway,
And it's probably just part of that system,
yeah.
that
Well,
circuit.
at least we know what the acronym means. I'm not sure we completely understand it, but I think we made some progress. Automatic disconnection of supply. Okay. Okay. This is pretty important. And so question 8: which of the following turbines is most likely to produce the greatest amount of torque?
It makes sense.
Yeah. So here the deal with that is, I think I've covered this before, is if we're just going to look head on into a wind turbine, let's just say we got a 3-blader going here, and a I don't know, something with a bunch more blades over here. And we're just looking head on into this thing. It's kind of a nasty looking turbine, but and they're both gonna spin, right? The whole point, and so let's just say that the two, this is going to be D1, the diameter of the first one. This is going to be D2, the diameter of the second one. The whole point is that when wind blows through both of these, initially, a lot of the wind is like literally just going to blow through and not hit anything. Whereas in the one with a larger number of blades, chances are that wind is going to hit a blade and do some work for you, and it's going to do it at a lower speed because the wind just didn't blow through. So if we look at it, any blade, I'm just going to write it like this. The torque is going to be higher on this one, and the torque is going to be lower on this one.
I thought that's what the question was.
Yeah.
Yeah, large.
Which of the following turbines is most likely to produce the greatest amount of torque?
Oh, why did I put large
Yeah,
turbine
I
with
put the
large
same-
number of blades?
yeah.
God.
I put the same. I did the same thing.
So there's only
The concept is there.
So you had
I
so
wasn't thinking about the turbine. I was just like, oh yeah, way more surface area with a lot of blades.
It's like, oh yeah, lots of blades. Bam.
well okay, so that was you just weren't careful. You just weren't careful. Okay, so let me draw it out here. Sounds like you knew what you were doing. You just made it. So here's
That far, but-
here's
After those other questions, I was just like,
Sam.
here's
question.
Nailed it.
so here's small. It's okay. Here's small and few up here. See small, few, and here's small, many. Here's big, few. And here's big, many. Those are your four choices, more or less. Small and few, that's A. Small with a large, this is B. Large with large, that's C. And then large with few, that's D. So I kind of gave you those four choices, and the question was, which is going to give you the most torque? And it's got to be the big boy, because it's the same thing as using a breaker bar to break free a rusted bolt. So okay,
Get some points for
I'll give you
stupidity, like,
yeah, courtesy points there. In fact, I can say, well, it's
It's half right.
half right. It is half right. It is half right.
I mean, it has more torque than the small turbine with 3 blades.
It does. Yes, it
So
does.
it's not the worst answer.
It does. Okay. All right. This one's nasty too, and I feel bad, man. 'Cause we don't really have enough lectures to cover this thing. 'Cause we were hijacked by the whole dang. I'll give you some shot at redemption here. Why might a two-bladed turbine that is yawing into the wind do so in a jerky manner? Okay. Let me just see what you write.
I thought I nailed it.
You might have.
I think I got it right too.
It could jerk into the wind due to the weight extended to the sides of the turbine from the blade. Yeah, that's similar, yeah. This weight is hard to swivel around the blades and to the side. If vertical, good answer, man. Absolutely, yeah. I call this the Dorothy Hamill effect. I don't know. Do you guys remember? You remember ice skating, right? So what's going on? And what you wrote there, Corey, is exactly right. Come here. So if we've got here's your tower again, and if the blades are like so, vertical, and the whole thing is spinning now about the it's spinning about its own little axis here, right? But it's also, let me try to draw that a little flatter. I'm trying to draw this line so it's more in the horizontal plane. Draw that a little flatter down here. So as it's turning, I don't know how it's floating up there. It's not attached to anything. As it's turning, this guy, what's that angle called? I'm just gonna call it psi for the lack of a better one. Versus this scenario. Yeah, it's still doing its little spin about its axis, but it's also spinning about this axis. Jeez, this thing's getting nasty. So I gotta get a 3D pad here at some point. So you can see that this is arms in, and this is arms out. So this guy, we'll just call that psi I for in. This is going to be psi O for out. And actually what it is, it's how quickly it's going. So I'm going to put a little dot over there. So it's how quickly that angle is turning. I think we all know that psi dot in is going to be greater than psi dot out, because Dorothy Hamill spins faster when her arms are over her head than we're sticking out. But the problem is, as psi is changing, so is omega. It's almost like your hands are going in and out. So that's the jerky motion. And I think you got that one right. Good. So I'm glad to see that. Select the statement that most accurately represents reality. Relative wind velocity is the vector sum of the real wind velocity through the turbine and the head wind velocity of the blade tip. Yeah, and that makes sense. Did we spend much time covering vector sums? Yeah, maybe a little bit. Let's just do it. Do you guys have another 5 minutes to hang out? 10:30, does that work?
Mm-hmm.
Okay. So what's the best angle to draw this one from? This one's tough. I mean, this one kind of has to be 3D as well. So I'll do my best to draw a turbine blade in 3D. I'm just going to do a two-bladed system.
The 102 book has a pretty
It
decent.
does, actually. Yeah, NRGY 102 has a pretty good vector sum in there. So what we're looking at is, so first of all, a vector. I'm just going to write V for vector. You can also think of V for velocity. I mean, it equals V sub x, so it's however fast that thing is moving in the x direction, and sometimes with a little I hat, and the I hat is just a pointing vector that has a unit length of 1. And that's all it is. It's just your index finger pointing in the x direction. That's all it is. Plus V sub y, j hat, and j is just pointing in the y direction, plus V sub z, k hat. And so the way to think about that is like so. You've got your x, you've got your y, and you've got your z, and they're all mutually perpendicular. X is perpendicular to y is perpendicular to z is perpendicular to x, etc. These little guys, these little I hat, j hat, and k hat, they're just kind of sitting down here. Here's I hat, and all it is just one little arrow pointing in the x direction. This is the j hat, and this is the k hat. And so they always, so what I'm going to write is the length, and I'm going to write the absolute value. So the absolute value, the length of I, just equals 1. That's how long it is. But the thing to keep in mind is that I is always pointing in the x direction. So, but the same thing with j. So they're just called the unit vectors. Now, if we look, we can just say now that v wind, we'll just say that equals, now I've drawn y over here. I'm just going to say that, let's just say that equals 5 j hat. And what that means is that the wind is only blowing in the y direction. And you could say, well, what direction is y? Well, it's west. Y is west, which means that x is going to be north. So you can sort of take those coordinates and put them wherever you like. And now, in this case, though, the tip of the blade, and let's see, what direction is that going? X is kind of into the page. At the very top, like at the very tip top of this guy, if this thing's really hauling, we can say that V tip equals, let's just say 10 I. And the arrow, well, I'm not that happy with how the arrow's pointing. I'd like to show you that it's like pointing in the x direction. I'll try to make it parallel to that x direction. But now, let's just say that the tip's over here, and we'll just look at this guy over here. If it's still spinning at the same direction, V tip equals 10 k hat. Does that make sense? Like it's still okay. All right, I'll do it with my hands here. It might be easier with my hands. So this is my fingers are the turbine blades, right? And I'm just gonna put them like this, and then the wind is blowing in from the Y direction, and you can see that's the horizontal. It's the left to right direction, basically. Left, so Y is left to right, and at the top, my fingers are kind of moving towards you, and that's that X direction that's coming out of the page. See that? And let's just say that the tip of this blade is, so the wind's blowing at 5 miles per hour, for the sake of argument, and then the tip's going at 10 miles per hour. So here comes your wind in at 5. This tippy top blade is now doing 10, but in the X direction. But once it gets down here, or all the way around, and positive and negative doesn't make that much difference. Once it's over here, now it's going 10 in the Z direction. So it's changing all the time. And so there's a component to that the 10 isn't changing. It's just that, oh, where is it pointing? Well, now it's pointing in the I, now it's pointing in the Z, now some combination. Turns out that it ends up being sinusoidal, as you might expect. But at any given time, V relative, this is how, and Einstein dealt with this crap all the time. And this is except he had, instead of wind blowing around, he had light bouncing around. So V relative just equals V wind plus V tip, and so we could just say, so up here, V relative equals, 5 j hat plus 10 I hat. Over here, V relative equals 5 j hat plus 10 k hat. So that's how you write a vector. You have to write out all 3 components.
But you could switch k hat and I hat as long as the 10's the same, correct?
You could, yeah. There's nothing special about what direction k hat and I hat are pointing, as long as they're perpendicular to each other.
Okay.
Yeah, as long as they're perpendicular. That's the whole point of setting those little guys up, so that you can talk about where exactly you are. If you're trying to land your spaceship on Mars, you're going to want to know, oh, are you operating in Martian coordinates or in spacecraft coordinates? Because up from Mars can be very different from up in your spaceship. You'd like to keep them pointing the same direction. So in some cases it does matter a lot. In this case, not so much, as long as you get the concept. Okay. These look all pretty good. So T is thrust, A is rotor area, big P is shaft power, little rho is air density, U is wind speed at the rotor plane. This must have come out of JAW.
Yeah, I found some,
Yeah.
I did some searching, but I did find them all.
Yeah.
Actually.
Good. And this is just so that you go through the book, and when you look at R, you're not thinking, oh, what is that, radiation, resistance? Well, no, it's the radius of the rotor, and obviously we only have 26 letters at our disposal, so you kind of have to make the most of them. I guess another 20 if you count the Greek letters, but that's just kind of look through the book. So I think, is that, that's good. I'll give you credit here. Whoops. Give you full credit on that guy. I'm not liking the way Moodle's going, man. I gotta say. This one I'll give you a little bit for the college try. That was not an easy question at all. And then, but it's really, I mean, this is going to be one of those things that's going to come up over and over again in any solar thermal system. So it's important to know. And then, oh yeah, I said I'd give you some credit there. Okay. All right, so is that everything?
Yeah.
Yeah.
Oh wait, no, that question with the
The
That
jerking?
one right there.
Yeah, I gave you a
Oh, you
full,
did?
I gave you a full
Okay.
point with that. Yeah, it's kind of hard to see, it's way down there, but I gave you a point. Okay, so at long last, we're moving through the important parts of the course. Sorry, it's been such a pain in the butt, but I think overall the projects are going well. I saw that Carson's all excited. He got his building going over the weekend. It's cool. What else? I think I gave you a fairly good overview. I think today's lecture is I'm gonna hold you guys accountable on the final for what I went over in lecture here today. So some pretty key concepts we went over. The only thing you missed there, Joe, we just kind of went over the variables, and those were mostly out of JAW. And then Adam, I'll respond to your concern about the question from JAW that was in chapter 4, and I think there's one pretty pesky diagram in here that well, I can't remember which one I wanted. It might have been figure 4.1. I think it's this guy, but I'll make a scanned copy of that. I'll knock that question off of quiz 3 and then hold you accountable for the final. So you'll be able to see this information when you take the final. Okay, I think we covered it pretty well. It was good quiz. 30 minutes done.